So, we were discussing this least square problem, basically using this technique of optimization to try to find a solution to Ax equal to b. Now, if you remember, we have shown that any critical point of this function is a solution, is a minimum to this function, and hence is a and hence is a solution to the original problem. So, any critical point of this problem is a solution to this problem. In fact, it is only critical one, it has all critical points should satisfy this equation. So, these are sometimes called normal equations. Okay. And if you remember what we had shown, that any x star which satisfies this one will satisfy Ax equal to b, that is what we had proved in the board. So, basically to find an x star which satisfies Ax star equal to b, we basically have to solve an equation like this, that is we should have x star equal to, of course this is only true when rank of A is n, it is a full column rank, m has the row has to, number of rows has to be more than n. So, it should have, so basically my x should have this expression. So, this expression A transpose is sometimes called the generalized inverse of A or pseudo inverse of A. Now, what sort of an algorithm would actually work for the least square problem? In general, let me let me tell you that the least square problem has the following form, that this discussion that we were doing in the last class were just an demonstration of how optimization in the form of minimizing a square. So, the least square, minimum square can be used to really solve problems of solving linear system of linear equations. So, least square problem is essentially trying to minimize a function f x which itself is expressed as a sum of squares. An explanation of the use, so I want to minimize over x element of R n. So, an example of such thing comes possibly in regression. In regression analysis in statistics, this is the least square method is a quite a chosen method. So, what happens, one of the problem is that you are given certain points, say of the form Ti Bi, time and positions of a person. Now, what sort of curve will it fit? Can I fit a straight line to explain the relationship between Ti and Bi, that is whether Ti and Bi has certain relation, or there is some curve like this that will be a better fit. So, there is a whole subject called curve fitting, and that is also useful in statistics. That is exactly what you do in regression analysis. You try first, the basic problem is to you first try to fit a straight line, and then you really want to minimize the error, square of the error that you would get if you use the straight line instead. And if you just assume that these points actually should have a linear relationship, that is they would lie in some straight line. Okay. So, curve fitting is a very important area. The curve fitting has important applications. Now, so suppose I have all these points of the form Ti Bi, it is obtained by some experiment and of course some physical experiment or some statistical experiment. So, we want to see where B, how B is related to T and X here is essentially the parameter. If you want to fit a straight line, that is if you want to say B is A T plus C, suppose you want a relationship like this, then this is your phi AC T. In fact, AC here plays the role of X. Okay. Now, once that is done, these n set of parameters X should be ideally chosen. The parameters X should be ideally chosen in such a way that at every Ti the function value should be Bi. So, suppose I have just generated m points here, but the number of points I generate, for example, in 2-dimensional, so you just suppose I am in 2 dimension and the number of points I have generated is just 2, then of course you can say they lie on a straight line. Maybe actually the relationships are not that when we run the experiment. So, experiments has to be run much more times than the dimension of the decision variables. So, the number of parameters here, whatever be the number of parameters, suppose n is the number of parameters, usually in a well posed setting m should be much larger than m. Actually, I should say m, this is way of telling m is much larger than. See, due to experimental errors or whatever, these conditions need not match exactly. So, what I conclude is that I compute some residuals. So, these are, so I find an x which will minimize these residuals, not really these residuals, but the sum of the squares of these residuals. So, I will put so for each I am having one residual. So, and then I want to minimize this over x in Rn. And this is nothing but if you take a vector Rx. So, if you take Rx, that is nothing but, sorry, the square of the Euclidean norm of R. So, basically you have to minimize this function over Rn, right. So, this is a very important example where least square techniques are of useful. So, statistics for example is one of the very important areas where least square techniques are indeed very useful. So, now we are going to see what sort of a algorithm one might use when one tries to do a least square method. Okay. So, this algorithm is essentially what we call the Gauss-Newton method. So, it is some sort of a Newton method, but modified by Gauss. So, it is called the Gauss-Newton method. Now, if I want to minimize the sum of squares, that is now f x, first I really have to find a critical point. So, I need to compute the gradient of grad f x, which is this is what you will have. This is a very simple thing, this is an application of chain rule at this point. Now, you observe that here what one needs to do is that you can express this in slightly better way. You know what is the Jacobian matrix. So, Jacobian matrix Jx of the vector Rx. So, if you, so basically taking the grad of f, grad of Rix. So, if you look at this, let me write down the Jacobian matrix. Jacobian matrix is a matrix whose first row is, so is a gradient vector now written as a row vector. Now, once you have this, if you know simple matrix multiplication, then you would realize that R grad Rix, so Jx transpose is a matrix whose column is, first column is gradient of R1x. See, we are always writing things as column vectors. Now, this simply means I can write this as twice of Jx transpose, if you know simple multiplication, Rx. So, once that is done, I would leave you as homework the following computation, is a computation of the Jacobian matrix, a Hessian matrix of f. So, which we usually write like this, or now for simplicity you can also write as Hx, which is equal to twice of okay. So, this will be homework for you. Now, if I want to use the Newton's method, then I really have to compute all these things. Basically, I have to compute the Hessian of each of the Rix at every point. So, that will be too much of a hazard, not a hazard I would say, but I would say that it is too much of a computational effort. But instead of doing so, I can use some sort of heuristics, means not heuristics, I do some little bit of tuning here, and then I say okay, let me not take Hx, the Hessian matrix itself, but some sort of approximation of it. So, I take the Hx is almost this. So, I do not do the second derivative at all, because this Jx depends on the first derivatives. So, what I am trying to do, I do not intend to use second order information in a place where I should have used second order information, but use first order information to force in an algorithm which is as effective as the one which you would have if you had taken in the second order information. So, this is some sort of a heuristic step. This term heuristics is very common in optimization, and nowadays many people who know, for example, have heard about genetic algorithms, which is also heuristics, but I would not go immediately for algorithms which are not supported by mathematics, because mathematics gives you the strength and it tells you how an algorithm would actually behave. And so, when you really see a problem of a particular type, you can know that which algorithm would actually fit this scenario. So, this is okay, let us say this is something called a heuristic step. So, we are basically ignoring this part now, the second order part. So, we are with only this information, we are going to now construct a technique which would actually give me, would lead me to the solution. Now, the Gauss-Newton method says okay, I will just do the following. Okay, you should be able to put 2 here, but 2 is of course does not make much of a difference just. So, this is actually acting as some sort of an approximation, this one as some sort of an approximation to your. So, it is acting as a approximation to your Hessian matrix. Now, how do I know that such an inverse would actually exist? So, you have to know that Jx transpose Jx, Jx has how many rows? M, and it has n grad R1 x, x is from Ri is from Rn to, so these Ri's are from Rn to R, which is clear of course from the expansion, we are not getting to all this every time. So, which means that there are n rows. So, now if all these n rows form a linearly independent set of vectors, right, then only the factor 2 here actually does not matter, because here you have factor 2, and then here if you take the inverse of this, so factor 2, if you take inverse of this, then you have to take inverse of 2, which is half. So, that will cancel out. So, it does not matter. So, do not get bother about the 2 here, the 2 will cancel out. So, here in the Gauss-Newton step, what we should have is that we should also have that for each x, Jx is of rank n. That would guarantee, if Jx is of rank. So, now here we have written down this heuristic step, and then we will take the Gauss-Newton, we will write down the Gauss-Newton iteration, which is xk plus 1 is xk. Now, instead of grad f square x inverse, I have here hxk, that iteration. Now, of course, what we need to do is to assume that this is each x, Jx is of rank n, then this inversion formula. So, the fact that the rank of Jx is n would guarantee the following. So, in order to have the fact that this matrix becomes invertible. So, we can write some sort of a Newton step. We have taken that the rank is n. So, we want this to be invertible. So, the required condition is that this would be of rank n, which we already have mentioned in the last page. So, this leads to the Gauss-Newton method, which is basically some sort of heuristical Newton method specifically done for this least square problem. So, we will let us write down the Gauss-Newton method. In the Gauss-Newton method, the interesting part is the following. The interesting part is that here we write everything just like a Newton method, and we expect the Hessian matrix to be this one. We think that that is the Hessian matrix. If that was the Hessian matrix, so we would expect a algorithmic iterative scheme of this form. So, the Hessian is twice of this. Now, if I take the inverse, that will become half. So, into the derivative, that is twice of j x k transpose r x k, and this cancels out to give me x k plus 1 is x k minus this one into that one, 2 to be cancelling out. So, this is the Gauss-Newton iteration. Now, in general you might think that okay, what would happen if this is not invertible? What can I do? If then we can create what is called a damped Gauss-Newton scheme, which is as follows. Basically, you can write this one. If you look at it very carefully, I can write j x k transpose j x k, this matrix operating on the vector x k plus 1 minus 1 x k is equal to minus of j x k transpose r x k. So, we can tell that this difference is nothing but decay, the direction of, or it is some alpha times decay. So, in general the idea would be the following. So, that let us write down what is called the damped Gauss-Newton method. Damped Gauss-Newton method. The idea is now to solve this equation. This is the first step. Now, find lambda k such that, so I get a complete descent f of x k plus lambda k dk, that is my x k plus 1 must be strictly less than f x k, and then basically you set x k plus 1 to x k plus lambda k dk. Now, the question is, will this be a descent direction? The question is, will this be a descent direction? So, you can take this as homework. So, if I call this as equation A here for example. So, is dk the solution of equation A a descent direction? That is very important to know. Of course, if you write dk as inverse of this, then that will become descent direction, that is immaterial. But in general, can you show it to be a descent direction? Kindly take this down as an homework. So, once you know this, I will give you an additional example to work on, homework example to try out the Gauss-Newton method. You can even run it on your computer writing programs. So, consider f of So, this is my least square problem. I have to minimize this. Of course, R1 x1 x2 in this case is root 2 and now of course, the Jacobian, which is the Jacobian of these two vector functions, Jacobian of the vector function R whose components are these R1 and R2. The Jacobian is given as is Jx basically, in this case x is x1 x2. So, this is of rank 2, this is J x1 x2 is of rank 2 when x1 is not equal to 2. If x1 is equal to 2, this will become 0. So, there will be column vector would be 0 0. So, so 2 3 and 0 0 would be linearly dependent, and so you cannot have you cannot have a 0 vector in the set of linearly independent vectors. So, hence if x1 is not equal to 2, then you can obviously have so you start with points x1 x2, never take x1 x2 to be x1 to be 2, and if you start with those points, then if your starting point is that and then your Jacobian is invertible. You have to make sure that your Jacobian is never x1 is never 2, then your Jacobian stops being invertible. Okay. So, now try out this procedure using the Gauss-Newton method, and you can also try out the damped Gauss-Newton and see what happens. So, we can talk about something later on, but we can now look at our program ahead, means what are we going to learn and discuss ahead. So, in the case of solving unconstant optimization problem, we have two important methods left, rather three important methods, but first we are going to just do the two more important ones, not more important, rather very popular ones. Quasi-Newton method, number 2 trust region method. The surprising thing about these two methods is that even if they are talking about unconstrained optimization problem, in order to develop these methods we need constrained optimization. So, we need very special types of constrained optimization problems. So, without a better understanding of constrained optimization and the Karush-Kuhn-Tucker conditions, which are as the necessary or sufficient conditions for differentiable optimization problems with constraints, it is not possible to get a correct idea of these methods. So, the idea is the following, that we in the coming lectures study in detail the Karush-Kuhn-Tucker conditions. And the quasi-Newton method and the trust region method would be done as an example of the application of the Karush-Kuhn-Tucker conditions or the ideas of constraint optimization. So, this is what is very example very important, and so we will start tomorrow studying the central issue of optimization theory, that is optimality itself. How do I characterize a point if I know that it is a local optimal to a constraint optimization problem? So, that is the first question. How do I characterize a point if I know it is a local minimum of a constrained optimization problem? The text that we are going to largely follow here is the following. Is a fabulous book called The Foundations of Optimization. Only we will talk about the differentiable case, we will not go into the non-differentiable case at all. And that will cover at least 10 lectures would be needed to complete Karush-Kuhn-Tucker conditions. I would just say possibly for the next 10 lectures we will really be bothered about knowing about the Karush-Kuhn-Tucker conditions. We will solve examples, and those examples will be very important and very important examples as far as optimization goes. So, this is a book by Osman Guler, a very famous optimizer. Works in the US, of course, in University of Maryland at Baltimore, Maryland at Baltimore. And this book was published by Springer under the GTM series or the Graduate Text in Mathematics series in 2011, I suppose. So, this is anybody who is looking at optimization from a certainly higher point of view from the graduate perspective should really go for this book. I would rather say that if you look at the NPTEL website, I find that there are other courses catering to optimization and operations research. Those who would be just bothered about knowing some techniques of how to compute a problem in various situations and not really knowing about the deep issues involved, the mathematical issues involved in optimization, then I would rather tell you to concentrate on those courses rather than concentrating on this course, because this course is given slightly at a graduate level, or rather you can say quite a bit of stuff would be at the graduate level. So, we would really like you to get involved and know the mathematics behind optimization. So, this course is essentially telling you the math behind optimization, not just telling you okay, there is a problem, you do this, what you will get, call it a solution. The point is that in most algorithms what you will get, you can never call it a solution. The art of optimization is to know that how good is your solution, how can you estimate the goodness of your solution. So, how do you do that? That is also a story which we will tell you in the form of a section called error bounds, which will come later on. Okay. So, here we stop, and here we from tomorrow we start Karush-Kuntaker condition. We talk about the history. First we start with the Fridtjof condition, inequality constraints, the type of problems are which come in those sort of cases. We can talk about, then we talk about both equality, inequality constraints, how to really get those conditions. You might think that okay, I have learned Lagrange multiplier rules in calculus, whether that is doing something with constant optimization, but there you never learned that you really have to guarantee the existence of such a multiplier, so that the actual solution of the problem is nothing but a critical point of the Lagrangian of the function. Such a thing has to be guaranteed, and here we show such things, right. So, we stop here, and I would rather say that this course would be given from this point onwards. It was earlier, if you look at the other things, it was given at quite a simple level. It will not be, I understand, but I wanted to keep this course very simple, but in order to give you a much more in-depth view of optimization, to really tell you what optimization is all about, what the hell is actually going on, you need to know the math deeply, you understand the math properly. I am afraid possibly many of you would like to shy away from mathematics, but I am afraid optimization is a mathematical subject, and a deeper idea about optimization is not possible without a understanding of its mathematical principles. Thank you very much.